Have you ever stopped to think where all that carbon dioxide actually goes? Once it's released from our cars, our factories.
Yeah, we hear so much about the emissions themselves, right? But less about the destination.
Exactly. And here's something quite interesting. A surprising amount doesn't just, vanish. It gets absorbed by our planet's natural systems.
And that includes places you might not immediately think of, like inland water bodies, lakes, rivers.
Right. These often overlooked carbon sinks. They play this silent but absolutely vital role in moderating our climate. They're like these hidden allies.
Totally. Hidden allies against rising temperatures.
It's true. And today, we're taking a deep dive into a fascinating new study. It uses a really cutting-edge approach, an integrated one.
Ah, okay.
To understand how climate change is specifically impacting the CO2 sink capacity of a unique man-made ecosystem in Egypt's western desert, the Wadi El Rayyan Lakes.
Oh, interesting. Man-made, you say, and in a desert environment.
Yeah. So our mission for you on this deep dive is to explore, how these lakes currently function as CO2 sinks.
Okay.
What the science is now predicting for their future capacity, say by 2050, under different climate change scenarios.
Right. The different RCPs, probably.
Exactly. And what surprising kind of interconnected implications this all has. For the global climate, yes, but also for the health of these specific unique water bodies.
And I imagine there are implications for managing them, too.
Absolutely. We'll even get into some innovative ideas for managing them. Because as you'll discover, local action in places like this, it can have global ripple effects. So let's unpack this.
Sounds good. So maybe let's start with the basics, just to make sure we're all on the same page.
Oh.
What exactly is a CO2 sink?
Good point. Broadly, it's just anything that absorbs carbon dioxide from the atmosphere, right? So it reduces the concentration up there.
Exactly. Forests, soil, they often come to mind first.
Yeah, the usual suspects.
But water bodies, from the huge oceans down to smaller lakes like the ones we're discussing, they are incredibly significant players in this.
So how do they actually do it? How do these water bodies pull off this feat of absorption?
Well, it's partly a chemical process. Water itself dissolves CO2 directly from the air.
Okay.
That forms carbonic acid, H2CO3, which then kind of breaks down further into bicarbonates and carbonate.
Right, the carbonate system.
Exactly. And those reactions are really sensitive to things like temperature, the water's pH, and obviously how much CO2 is in the atmosphere to begin with.
And it's not just chemistry, is it? There's a biological element, too.
Definitely. You've got tiny organisms, phytoplankton, living in the water. They act like tiny plants, basically.
So they use photosynthesis.
Precisely. They consume CO2 for photosynthesis and release oxygen, just like trees, but, microscopic and in the water.
What I found really eye-opening was this fact. Apparently, water bodies absorb roughly a quarter of all the CO2 we humans emit each year.
It's a staggering amount, isn't it? A quarter. That's huge.
It really is. A massive, often kind of unheralded contribution to keeping global temperatures in check.
It genuinely is, and this highlights a critical sort of two-way relationship, a feedback loop almost.
How so?
Well, the water bodies absorb CO2, which helps slow down climate change, but climate change itself, rising temperatures, changing weather patterns, directly affects their ability to keep doing that job.
Oh, right. It's a mutual dynamic thing.
Exactly. An intricate dance, you could say.
So if water bodies are soaking up all this CO2, what are the key factors that determine, how much they can actually absorb and hold on to?
The big ones are water temperature, salinity, how salty the water is, and the sheer volume of water, how much water is actually there.
Okay, temperature, salinity, volume.
And the crucial thing is, all three of those are highly sensitive to climate conditions.
Right, so like warmer water.
Warmer water holds less dissolved gas. That includes CO2. So as water temperature goes up, CO2 solubility goes down.
Less capacity. And evaporation. That must affect the volume.
Directly. Increased evaporation shrinks the water body, reducing the overall size of the sink.
Okay, that makes sense. So with that foundation, let's zoom in on the specific focus here. The Wadi El Rayyan Lakes. You said they're unusual.
They absolutely are. So Wadi El Rayyan is actually two man-made lakes. They're located in the hyper-arid western desert of Egypt near the Fayum Oasis.
Hyper-arid meaning extremely dry and hot.
Extremely dry. Very hot, yes. And their origin story is quite unique. They weren't always there.
Right. You said man-made. How did they form?
It started back in 1973. Agricultural wastewater, drainage water basically, was diverted into a natural depression in the desert.
Okay.
That created the first lake, the upper lake. Then around 1980, the surplus water from that upper lake started overflowing, actually through a waterfall.
A waterfall in the desert.
Yeah, and that formed the second lower lake.
Wow. So entirely artificial, fed mainly by farm runoff. That's a fascinating setup. What else makes them distinct?
Well, their physical characteristics are quite different. The upper lake's surface is about 10 meters below mean sea level.
Minus 10 meters.
Yeah. While the lower lake is even deeper, down at minus 32 meters.
Okay.
But the really striking difference is salinity. The upper lake is relatively fresh, averaging around 1.6 parts per thousand, or ppt.
Which is pretty low, right, compared to the ocean?
Very low. Ocean water is typically around 35 ppt, but the lower lake, it averages around 15.6 ppt, much saltier.
Okay, so 1.6 versus 15.6, that's a huge difference, almost 10 times saltier.
It is. And it implies you've got two very distinct ecosystems operating essentially side by side within this linked system.
And the climate, you mentioned hyper-arid, super high evaporation rates, I guess.
Incredibly high, often exceeding 4.65 millimeters per day on average, and very, very little rainfall.
Wow, that must put immense pressure on the water levels.
It does. The main water source is the Wadi Grain, that agricultural drainage flowing into the upper lake.
Right.
The lower lake then gets its water basically from the upper lake's overflow. And evaporation, given that climate, is the main way water leaves the system.
Are there other factors?
Yeah, there are some pump stations, fish farms too. They influence water levels to some extent.
Okay, this whole setup is really quite remarkable. But it begs the question, why study these particular lakes? What makes them so important for understanding climate change, especially since they're artificial?
That's a great question. This study is actually considered the first of its kind.
Oh, really?
Yeah, the first research to really dig into CO2 sink capacity changes under future climate scenarios, specifically for inland waters in the Middle East. And the fact that it uses this novel integrated approach makes the findings really significant, potentially quite broadly applicable.
Okay, let's talk about that integrated approach then. How did the researchers actually go about modeling the future of these CO2 sinks? It sounds complicated.
It is quite complex, yeah. They essentially combine three powerful analytical tools. First, CO2 solubility modeling.
Okay.
Second, hydrodynamic simulations using a specific software called Delft 3D FLO. And third, GIS analysis, geographical information systems. This integrated approach is really critical because it lets them look at how multiple factors interact to predict the impact on CO2 sink capacity.
Okay, let's break that down. The CO2 solubility modeling first. What does that involve exactly?
So this part is about precisely quantifying how much CO2 can dissolve in the water. And as we said, that mainly depends on temperature and salinity.
Assuming constant atmospheric pressure and CO2 levels.
Exactly. They assumed constant CO2 partial pressure, about 0.04%, and standard air pressure. Then they used existing data from tables showing solubility at different temperatures and salinities to build a mathematical model.
Okay.
And it was a nonlinear model, very precise. They got a correlation coefficient, R squared, of 0.99886.
Wow, that's almost perfect correlation.
It's incredibly high. It gave them really strong confidence that their model could accurately predict CO2 solubility based on changing temperature and salinity.
Okay, so they built this highly accurate equation for solubility, and then they fed that into the hydrodynamic model, creating a sort of digital twin of the lakes.
Precisely. They used Delft 3D FLOW. It's an open source tool, widely used, kind of an industry standard for modeling lake hydrodynamics. Okay. They set it up as a two-dimensional or 2D model that simplifies the calculations a bit but maintains the accuracy needed for the study. They simulated a whole year, like Feb 2013 to Jan 2014, for example.
And what did that simulation include?
It took into account all the critical forces, salinity variations, temperature changes, wind effects, and of course, all the water coming in and going out.
It sounds incredibly detailed, but how did they make sure the model was actually, reliable, that it matched reality?
That's crucial. Through rigorous calibration and validation.
Good.
They compared the model's outputs, things like predicted water level, temperature, salinity, against actual measurements taken from the lakes.
Real-world data.
Exactly. And then they meticulously adjusted the model parameters until its predictions matched the real-world data accurately. For instance, they realized they had to account for some minor water sources and losses that weren't initially recorded.
How did they adjust for that?
They ended up, for example, reducing the assumed inflow into the upper lake by about 10% in the model to make everything balance out correctly with the observed data. This kind of painstaking calibration is essential if you want to trust the model for making future predictions.
Okay, that makes sense. Rigorous process. And what about those future predictions then, out to 2050? How did they handle the uncertainty about future greenhouse gas emissions?
For that, they used what are called representative concentration pathways, or RCPs. You mentioned them earlier.
Right.
Specifically, they used two main ones, RCP 2.6 and RCP 8.5.
And what do those represent?
RCP 2.6 is basically the optimistic scenario. It represents a future where we achieve significant global emissions cuts, serious mitigation efforts.
The best case, sort of.
Pretty much. And RCP 8.5 is the other end of the spectrum. It's the pessimistic, high emission scenario, closer to a business as usual path if we don't make major changes.
Got it. Best case and worst case for the climate's impact on the lakes. What assumptions did the model make when running these future scenarios?
Some key ones. They assumed no major changes in the lake's surface area itself or in the surrounding agricultural lands or the fish farms.
Okay.
They also assumed the water inflow and intake rates remained consistent with the baseline period.
Why make those assumptions?
It was crucial to isolate the effect of climate change. By keeping those other factors constant, they could be sure that any predicted changes in the lake's condition were solely due to the changing climatic factors, temperature, evaporation, etc., driven by the RCP scenarios.
Okay, so focusing purely on the climate impact. And how did they actually run the prediction over that long period, 2020 to 2050?
They broke it down. They divided the 2020-2050 period into 10-year stages. And for each stage, they used the average predicted climatic data for that decade. Ah, okay. So average data for 2020-2030, then 2030-2040, and so on.
Exactly. That gives a more robust, smoothed-out long-term prediction, rather than trying to capture every single year's fluctuation.
Okay, the stage is perfectly set now. The models are built, validated, the scenarios are chosen. The big question, what do they actually find? What's projected to happen to these lakes by 2050? Let's start with, say, water depth and salinity.
Yeah, the projections are, well, they're quite concerning. The model predicts a really remarkable decrease in water depth for both lakes by 2050.
A drop in water level. Why?
Primarily due to increased evaporation rates driven by the rising temperatures in both RCP scenarios. The lower lake, in particular, is expected to experience the most significant loss of water.
Okay, less water. And as that water evaporates, what happens to the salt that's left behind?
Well, concentration goes up. Dramatically.
Right. Because you have that increased evaporation concentrating the salts, plus the continuous inflow of agricultural drainage water, which also carries some salts, without enough freshwater replenishment. Salinity is expected to increase remarkably.
How remarkably?
In the upper lake, salinity is predicted to increase by about 1 ppt, reaching around 2.5 ppt, still relatively fresh, but saltier than today.
Okay. But the lower lake, you said it was already much saltier.
Yes, and that's where the change is really severe. Its salinity could increase dramatically, potentially reaching as high as 60 ppt under the RCP 8.5 scenario.
60
parts per thousand, yes.
Wow. That's almost double its current salinity and way saltier than typical ocean water. That must have huge implications for its ability to absorb CO2.
Absolutely. When they looked at the estimated soluble CO2 in the water columns, how much CO2 the water can actually hold, several clear trends emerged.
Okay, like what?
Well, seasonally, it confirmed what we'd expect. February, which is winter there, shows the maximum capacity to absorb CO2 because the water is coldest.
Makes sense. Colder water, more solubility.
Exactly. And conversely, August, the peak of summer, has the minimum capacity because the warmer water just can't hold as much CO2.
Right. And between the two lakes, is there a difference in performance?
Yes, a consistent one. The upper lake is always a better CO2 sink than the lower lake.
Why is that?
Primarily because of its much lower salinity. Lower salinity enhances CO2 solubility. It's just easier for the CO2 to dissolve in fresher water.
Okay, so lower salinity helps. What about the overall trend over time? Comparing 2014 to the 2050 projections. Are they still effective sinks?
Well, that's the worrying part. There's a clear and substantial decline projected in the lake's overall capacity to dissolve CO2 from the atmosphere by 2050 compared to the 2014 baseline.
And that's mainly due to?
The projected increase in water temperature, climate change warming the water, is the primary driver, reducing their effectiveness.
Okay, so can we put some numbers on that? What's the overall projected loss in CO2 sink capacity for the whole Wadi El Rayyan system?
Okay, so by 2050, the lakes combined are expected to lose about 23% of their CO2 sink capacity under RCP 2.6. That's the better climate scenario, remember?
23% loss even in the best case.
Yes. And under RCP 8.5, the high emission scenario, They're projected to lose about 25% of their capacity compared to 2014.
A quarter of their carbon absorption power potentially gone in just a few decades. That's significant. And you mentioned earlier, it's not an even loss between the two lakes.
Not at all. And this is a really critical point. The vast majority of that loss, that 23 to 25% total reduction, is predicted to come disproportionately from the lower lake.
Okay, how does it break down?
The upper lake, the fresher one, is projected to see an average monthly loss of about 14% to 15% in its soluble CO2 capacity.
Still significant, but
But the lower lake faces a much, much more severe reduction, an average monthly loss projected at 46% to 47%.
nearly half.
Nearly half of its capacity gone by 2050. To put it another way, in 2014, the upper lake could dissolve roughly twice as much CO2 as the lower lake. By 2050, under these projections, the upper lake is expected to dissolve 4 times more than the lower lake. It really highlights how dramatically the lower lake's effectiveness is predicted to decline.
Wow, that's a huge shift in their individual roles. So what are the deeper implications of this massive loss, especially the near 50% reduction in the lower lake's capacity? It sounds like it could create some kind of, I don't know, vicious cycle.
You've hit on it exactly. It's a potential feedback loop. When the lakes absorb less CO2, more of it stays in the atmosphere.
Right, contributing to the greenhouse effect.
Which then causes atmospheric temperatures to rise further. That, in turn, increases the lake's surface water temperature even more.
Making them even less able to absorb CO2.
Precisely. Warmer water decreases CO2 solubility further, leading to even more CO2 staying in the atmosphere. It's a self-reinforcing loop, a positive feedback loop in climate terms.
And
Eventually, this kind of loop action could potentially flip the water body from being a beneficial CO2 sink into actually becoming a net CO2 source. It starts releasing CO2 instead of absorbing it.
so it goes from being part of the solution to part of the problem.
Exactly.
And beyond just the CO2 and the climate feedback, what does this warming and increased salinity mean for the actual life in the lakes? The fish, the plants, the organisms.
Yeah, that's the other critical impact. Increased water temperature doesn't just reduce dissolved CO2, it also crucially reduces dissolved oxygen.
Which is vital for aquatic life.
Absolutely essential. Low oxygen levels, or hypoxia, can severely disturb the aquatic biota. It affects fish growth, maturation, metabolism.
And in severe cases.
In severe cases, it can cause widespread mortality. It can fundamentally alter the entire ecosystem, potentially turning the lower lake, especially with that soaring salinity, into a much more barren, hypersaline environment, hostile to most of the current life forms.
This sounds like a really tough situation, a pretty dire outlook, especially for that lower lake. But the study didn't just diagnose the problem, right? It also proposed some solutions, some pathways to preservation.
It did, yes. They offered some management recommendations, focusing on tackling the root causes, evaporation, salinity, temperature.
Okay, what did they suggest for controlling evaporation, for instance?
They proposed both natural and technological solutions. On the natural side, they suggested planting wide canopy trees along the lake banks.
To provide shade.
Exactly. Shade the water surface. And also encouraging free-floating vegetation, like certain types of aquatic plants, on the water surface itself.
How would that help?
Both would reduce direct sunlight hitting the water, lowering temperature and thus evaporation. Plus, the plants themselves would consume CO2 through photosynthesis.
Ah, an added sink benefit.
Right. And they also suggest it could enhance water circulation due to creating temperature gradients and, add aesthetic value too.
Yeah.
Maybe even attract some ecotourism.
Okay, using nature to help nature. What about more technological approaches?
They suggested considering covering parts of the water surface with floating solar panels.
Floating solar. Interesting.
Yeah, it's a really neat multi-benefit idea. The panels block sunlight, which significantly decreases water surface temperature and limits evaporation.
Okay, same benefits as the plants and trees there.
Yes, but simultaneously they generate renewable energy, so it's a potential win-win. Water conservation and clean energy production.
That's a very innovative idea.
Yeah.
So controlling evaporation is one angle. What else did they recommend?
The other major recommendation was about increasing water inflow.
Adding more water back into the system.
Specifically, they emphasized the urgent need to seriously consider allowing more water from the Wadi drain, that agricultural drainage source, to flow into the upper lake.
Even though it carries some salts.
Yes, because the primary issue is the concentration effect from evaporation. Allowing more inflow would help compensate for the water lost to evaporation. And crucially, it would help slow down the rate of salinity increase, especially buffering the lower lake from becoming quite so hypersaline. It gives it a fighting chance.
Okay, so it's about balancing the water budget better. The core principle behind all these recommendations seems to be about maintaining the physical state of the water itself.
Precisely. The fundamental goal is to conserve water volume, decrease the water temperature, and control the rise in salinity. Because colder, fresher, and larger water bodies simply have a higher natural capacity to dissolve CO2. These strategies aim to keep the lakes functioning as effective carbon sinks, preventing them from succumbing to that vicious cycle and potentially flipping into becoming CO2 sources.
What a journey this has been. We've really unpacked this complex interplay between climate change and these inland water bodies. Using Wadi El Ryan is a really powerful and, frankly, quite concerning case study.
It really is. And it serves as such a stark reminder, doesn't it, that even ecosystems that seem remote, or even ones that are man-made like these, play a critical, interconnected role in the much larger global climate system.
Absolutely.
Yeah.
And that local management decisions, the kinds of things we just discussed, planting trees, maybe floating solar, adjusting water flow, they can actually have potentially far-reaching impacts on that global scale.
It shows that local action matters.
It really does. And as you, our listener, reflect on all this, maybe consider this final thought. As our planet continues to warm, how many other water bodies out there, perhaps much less studied than Wadi El Ryan, are silently losing their ability to absorb carbon right now?
That's a sobering thought.
How many might be nearing that tipping point, risking a shift from being a vital climate ally to becoming an additional climate challenge? What does this quiet, creeping change mean for our collective future?
And what other innovative solutions, like maybe the floating solar idea, might be out there, waiting to be explored and implemented to ensure these crucial ecosystems continue to work for us, not against us, in the years to come?